Good evening. Welcome to the first Watson Lecture of 2024. Woo. Yeah. Well, I hope you guys all had a chance to kind of catch some of the pre-show. Maybe you got a chance to talk with some of the researchers that work with Dr. Bethany Ehlmann, or meet some of our neighbors from across the street, the Pasadena City College Geology Club. We love being able to throw open our doors and welcome you, the community, to Caltech to hear about the amazing research that's happening on campus. But to start with, I'd like to give a special welcome to some of the students in the audience. Joining us are high school students from Santa Ana High School, and they're members of our Junior Watson program. So our Junior Watson program gets the opportunity to tour some of the labs at Caltech and, hear about some of the unique opportunities to study science and engineering here on campus. So we're really happy to have them with us tonight. I'm Crystal Dilworth. I'm a science communicator and a Caltech alum, and I've built a career communicating the connection between fundamental research and our everyday lives. And I'm really proud to be continuing that work as the host of this season's Watson Lectures. Today, we're going to be hearing from an amazing researcher, Dr. Bethany Ehlmann. But before that, I'd like to take you back in time, and we're going to explore some of the history of the Watson Lectures themselves. So if you can imagine with me going back to 1928, 8 years after an institution formerly known as Throop University was reimagined and renamed the California Institute of Technology. You might have come here to hear your Watson lecture on a bicycle, Pasadena Short Line, or if you're really fancy, maybe a Ford Model T. You definitely wouldn't be in this building. The entire campus north of San Pasqual didn't exist yet. And you would have heard some guy by the name of Linus Pauling give a talk on interesting phenomena in changes of physical state. Or maybe you would have heard the unfortunate story of nebulium, a speculative element that never quite made it on the periodic table. But you also would have heard about technologies that were about to significantly impact your lives. Talks with titles like Principles of Radio Communication or Principles of Heating and Ventilation. Pretty cool, right? You would have heard in that one year, 1928, you would have heard so many impactful talks from scientists that shaped the world that we live in today. But what you would not have heard is a talk by a woman. Now, Caltech and academia has come a long way from 1928. There's still work to be done, but I'm not here to talk about that. And so tonight, Dr. Bethany Ehlmann is going to join the ranks of many amazing female scientists that have presented the impactful research that they have been doing as a Watson Lecture speaker. But before we hear her talk, we're going to learn a little bit about her as a person. So you'll hear an introduction from Professor of Geophysics, Mark Simons, and you'll see a little bit of a pre-recording. So you learn a little bit more about her life and her work before you hear about her research. And then after her talk, that's when you guys get a chance to ask your burning questions. So a QR code will appear on the screen, and you can use your phone to submit questions to me, and then I will ask Dr. Ehlmann. We'll have a little bit of a Q&A. So make sure if there's any questions that come up when you're listening to her talk that you remember, because we want to get those answered. And then afterwards, of course, you're all welcome to join us for tea and coffee and additional conversation in the courtyard afterwards. Okay, I think that's all of the orders of business. So if you guys will take the opportunity to note your nearest exits, please turn off your cell phones or silence your watches, all of your tech that beeps. Okay, excellent. And allow me to welcome to the stage Professor of Geophysics, Dr. Mark Simons.
Wow. Good evening. Thank you for joining us tonight. The exploration of Earth and other bodies in the solar system is currently experiencing a revolution of sorts. Small, capable instruments aboard small satellites are being added to our quiver of tools that we can use to explore both Earth and other bodies in the solar system. Further, largely due to the commercial space industry, the access to space is increasing very quickly, right? So going forward, space exploration will not rely solely on billion-dollar spacecraft. We will see all these other smaller spacecraft as being very important tools for us going forwards. As you'll learn tonight, Professor Bethany Ehlmann is very much at the forefront of this revolution. So I thought I'd give you a little bit of a background on Professor Ehlmann. She got her undergrad at WashU in St. Louis. She has 3 master's degrees, 2 from Oxford, one in environmental change and management, and 1 in geomorphology. She then got a 3rd master's at Brown University, where she got her PhD in earth science. Following her time at Brown, she was then a Marie Curie Fellow in Paris, and then she's been with us here at Caltech for at least approximately 13 years. The list of awards she has received is so long, I'm not going to try to repeat them here. I think it's much more interesting, actually, and exciting to understand sort of the variety of science team and leadership roles she has had on space missions over the last several years. And I'll just list a few of them to give you some sense of the scope. There's the Dawn mission that visited the asteroid Ceres. Several missions to Mars, both landers and orbiters. Currently, the EMIT mission, which studies the distribution and composition of dust on Earth from the vantage point of the International Space Station. And of course, she's the PI of Lunar Trailblazer, which we'll hear much more about in a few minutes. Last year, she was appointed as the new director of the Keck Institute of Space Studies here at Caltech. We affectionately know it as KISS here. Professor Ehlmann is also the president of the board of the Planetary Society that is here in Pasadena, and I believe we have a lot of members of the Planetary Society here, so welcome. So it's also worth noting, I guess, that more than just the science, she is an avid traveler and outdoor enthusiast. And as you can tell, Professor Ehlmann has plenty of stories to tell. So I think we should just start and let her tell her story now. Thank you.
I grew up in Tallahassee, Florida, and I was fortunate to be surrounded by nature. I have always been interested by the natural world, fascinated by the stars, but also by ecology and botany and oceanography and those complex living and non-living natural systems that shape our world. It was that element of exploration and the natural world that really drew me to science in the first place. My name is Bethany Ehlmann. I'm a professor of planetary science at Caltech and director of Caltech's Keck Institute for Space Studies. My research work is focused on the exploration of the solar system, the moon, asteroids, Mars, and beyond. I got connected to planetary science through an amazing mentor of mine, Professor Ray Arvidson at Washington University in St. Louis. As an undergraduate, my first job was in the remote sensing laboratory. I was very fortunate to have the opportunity to actually work on a space mission, on the operations of Spirit and Opportunity, and then I was embedded with the science team for the next 6 months, helping to operate rovers. With Lunar Trailblazer, undergraduate students at Caltech and at Pasadena City College can be on the operations team, just as I was 20 years ago for Spirit and Opportunity. I explore planets of the solar system because I'm so fascinated about the histories that they hold and their potential today for having life. So I have been super excited to explore Mars. that has a history much like Earth, but an evolution path that at some point diverged. It went from warmer and wetter to cold and dry, and we don't really understand why, but in that why, there's something profound about how planets work that's incredibly exciting. People often ask me about my favorite planet, and the reality is my favorite planet is Earth. There's only one planet that we've found in the universe that has that unique combination of geology, atmosphere, ocean that allows and sustains life. The more we explore, the more I think we should realize how special our own planet is. I think what drives me to explore is in part a scientific impulse and a curiosity to know and understand what's out there. How did we get here? Are we alone in the universe? I think those are some of the most profound questions that anyone asks. I think also, though, space exploration in many ways brings out the best in us as a society, where we band together to do something that's hard, that's challenging, and that's really done for the purposes of knowledge, expanding that. So I love being a part. I think it's, some of the modern day cathedrals are our space exploration missions, these exquisite pieces of technology, but that are really just extensions of our human curiosity out into the solar system. All right, good evening, everyone, and thank you for coming to celebrate the science that we're doing here at Caltech, JPL, with our collaborators, and hearing about Lunar Trailblazer, our pioneering small satellite to study lunar water. You heard a little bit about how I got involved in planetary science, and it's really, captured very much in this photo from Apollo 8. How many of you were around when astronauts were on the moon? Yeah, a little less than half the audience. Okay. I love this photo, but man has not been on the moon in my lifetime, but yet it captures, I think, the essence of planetary science, which is why are we on this planet, this orb that has sustained life for 4.5 billion years, juxtaposed against our dry lunar surface. It really highlights how special things are. It also highlights what is out there in the solar system to continue our exploration. So I'm going to give you a talk in 3 parts, because it turns out the moon is not so dry as was believed. And so part 1 is going to talk about water on the moon. What are some of the predictions? What are some of the surprises? Then we're going to talk about what I think is a revolution that is almost exciting as Apollo. I think this is one of the best times to be a planetary scientist, is right now. And that's what's going on in terms of access to space, part of that being small satellites. And finally, the Lunar Trailblazer mission. So let's get going here. For part 1, water on the moon. I mean, this is not something you talk about when you, last time you stared up at the moon, did you think about water on the moon? Who did? Yeah. Yeah. And that is because the moon, it's against the vacuum of space, right? Water is not stable. Water is going to evaporate or sublimate into space. That's all the more the case because at our particular distance from the sun, an airless body, like the moon, is actually a surface of extremes, okay? We know the temperature fluctuations throughout the day on Earth. What I'm showing you here is, imagine that you are at one of these dots, either near the equator or at the pole. This is showing the temperature over the course of a lunar day as the sun is moving overhead. Now, a lunar day is about 14 days because of the orbital mechanics, so it takes a little longer. But if you're standing at the equator, you're going to experience these extreme temperatures well above boiling, down to, during the cold parts of the lunar night, significantly below freezing. And so in this environment, one would not expect liquid water. One would not expect solid water either. Ice, right? Ice is going to sublimate. Ice is going to into the vacuum of space. But some of you who might be looking at this might be looking at what's going on at the poles. It's a little more complicated. And this is where the water on the moon story gets interesting. Now, this story has a peculiar Caltech angle. This is Caltech, so I should highlight. Okay, note date on paper, 1961. So this is a long story. Graduate student Kenneth Watson and colleagues in the Division of Geological Sciences, note it wasn't geological and planetary sciences at this time, cited such luminaries as Urey, saying that they recognize that there may be depressions on the moon where the sun never shines. But at the time, these folks concluded that because of these temperature extremes, there would not be water, or there could not even be solid water that might have come in from a comet for any kind of period of time. But Watson here, in the course of his PhD, argues that water is actually far more stable on the lunar surface because of the extremely low temperatures and then the extremely low vapor pressure, which means that it's hard for the water to sublimate against the vacuum of space. Okay, so let's parse out, what does this paper mean? Well, first of all, there are depressions where the sun never shines on the moon. Why is this? Well, the moon is not very tilted on its axis. It's more or less straight up and down. And so if you're at the poles and you're in a depression at the poles, the animation here is showing that as you go through the course of the lunar day, there are places that the shadow never leaves the surface. There is no direct illumination of these locations. So there are truly places where the sun never shines on the surface of the moon. Now, we have sent spacecraft to measure the temperature of these surfaces and made exquisite maps. Dave Page at UCLA published this map from the Diviner instrument on the Lunar Reconnaissance Orbiter of what is the temperature in those regions on the moon. So that's what I'm showing over here on the side. You can see at the warm parts near the poles, it gets quite toasty. 300 Kelvin, so 30 degrees Celsius or so, balmy day. But in these places where the sun doesn't shine, it's 100 Kelvin. And what is being shown here are some of the volatiles, the ices that could be stable. So remember, what happens if you have you plucked a piece of ice and you put it on the moon? Maybe it was a piece of a comet that crashed, or asteroid that came in the moon, or it was some volcanic gas that erupted and then condensed on the surface. Like CO2 ice on Earth, it's going to sublimate against the vacuum of space. But if it's cold enough, this sublimation rate is so slow. How slow is it? It's so slow that it will only over 1 billion years sublimate a millimeter. So it's so cold that ice could sit there for 1 billion years and only lose 1 millimeter to space. So then when we look at this, then we can see that in these polar regions, many of them are below, the temperatures are low enough that they could have water ice. In fact, they could have all kinds of exotic ices delivered from comets or perhaps trapping the gases of ancient lunar volcanoes. Now, Lunar Trailblazer is not the first to investigate. The L-Cross mission was actually sent to crash into one of these regions. It crashed into Cabeus crater here. This is one of the permanently shadowed scarps in Cabeus, and this is the plume, this like gray is the plume of the L-Cross impactor. And then the CHASE, which was then observed by the CHASE spacecraft, capturing a spectrum that, if you do the modeling, had about 5 to 8% water ice coming out in this plume of dust and other materials. And since then, other missions have studied water on the moon as well. There are maps that show that there's hydrogen, H2O, right? You need the H. So there's hydrogen enrichments in some of the polar regions. In a few spectra, and the spectra are here, and this is very close to the signal-to-noise ratio, but in a few locations there have been direct detections where the infrared light reflecting on the surface has absorptions characteristic of water. But the state of the science is not so great at knowing exactly how much water and where it is. Note that the neutron estimates tell you there's maybe half a weight percent over a 100 square kilometer area. This puts an upper bound at 30 weight percent, but only 3.5% of the places there's this signature have this signature of ice. And some of the ice detections actually seem to be in the sun and not the shade, and that doesn't make a lot of sense, actually. And so the state of where exactly there is water on the moon and how much might be in these cold traps is at a very sort of unsettled state of science. Meanwhile, on Mercury, I love that as a planetary scientist I can say that. It's this glorious time where there are all these space missions to all these planetary bodies adding pieces of the puzzle. So Mercury, like the moon, orbits more or less straight up and down. So it too has these depressions. Even though it's hot, even though it's the closest planet to the sun, there are still places where the sun doesn't shine on Mercury, making these cold traps that can host water. And in fact, they were detected, and they were detected definitively. In some of these permanent shadows, radar deposits indicate water ice in these large, nearly pure deposits. And separately, this was confirmed by gamma ray data indicating hydrogen, and it's beneath a lag of organics. Someone else can give a whole talk on this, because there's a mystery here. Why is there so much ice on Mercury, and the evidence is a little squishier on the moon? So that's the state of the science as of right now. That's where we're at with understanding water on the moon. Now, a surprise that no one predicted also happened in 2008 with a different mission. This was the moon mineralogy mapper on the Chandrayaan spacecraft. So Chandrayaan was India's first mission to the moon. They sent an orbiter to the moon. They asked NASA, hey, NASA, do you want to put an instrument on it? NASA's like, yeah. So NASA carried the moon mineralogy mapper, which was a JPL-built instrument, and actually one of my professors at Brown University was the principal investigator, Carly Peters, of that instrument. What M-cubed revealed, moon mineralogy mapper M-cubed, when it started mapping is that as you move toward from the equator, remember the equator is very warm, to the cold, high latitudes, what it revealed is that this is reflected light as a function of wavelength. This dip kept getting stronger and stronger as you go toward the poles. So that's interesting. And what's particularly interesting is that in the lab, if you go take a spectrometer and you look at OH or H2O bound on a surface or ice, that is that same roll down. So we have these enrichments, even on the sunlit side of the moon, that actually gets really hot. Somehow there's this spectroscopic signature of water. Now, interestingly, it's not just as a function of latitude. There are a few rock formations, some associated with volcanoes. Here I'm showing an example associated with an impact crater that have that little absorption that indicates water enrichment. So is this a volcanic process? Is this pointing to water on the interior of the moon coming out and coming into these rocks? A different instrument, this was actually, for those of you who are space aficionados, this is the Deep Impact mission, had an extended mission. They were called IPAC for that. I don't know what the acronym stands for. But they flew by the moon, and when these data were coming out, they looked back at their data and said, hey, we see that water signature too. And they had multiple times of day that they had taken the measurement. And what you can see here is that it appears that this absorption is deeper, meaning more water in the morning, in the evening, but maybe it diminishes in the afternoon. So is the water coming and going on the sunlit side of the moon? How much? Well, how much is tricky, because the other thing that's happening is that there's a big thermal effect. Any of you know black body radiation? Yes, oh, okay, thank you. When you have black body radiation here, right, you get this upturn as a function of temperature. And so that's at exactly the place that this little absorption due to water is turning down. So knowing how much is a very tricky question, because you've got to disentangle these effects. So let me just show a graphic that explains this. So this is 180K, sorry, there's something covering this up, but this is that absorption due to water. You can see that as the moon's surface gets really hot, this absorption that you use to find OH and H2O, around 300 or so, it starts going away. It starts getting weaker. And that's because you're getting this black body radiation. This great graphic was produced by Emily Felder, one of our PCC undergraduate interns here for Lunar Trailblazer. So we've got some questions here. We know we have water on the moon. We don't know exactly how much. We don't know exactly how it varies with time. And we don't know actually exactly what it is. So far in this talk, I've been using water very loosely. Water. I should have been doing water. Here I'm showing that same spectrum again of what water looks like in the lab. But actually, water can mean a few things. There are at least 3 things that I'm encompassing in the term water. One is what we might classically think of, water ice. Okay, that could be in those cold regions of the moon. That has this characteristic of absorption signature here. Another thing that could happen, those of you who are on Earth know that like surfaces are sticky and like water can adhere, like water molecules. We're all like walking around with a layer of water molecules kind of on us. That loosely bound water, just H2O molecules on the surfaces of things, also creates a spectroscopic signature, as does simply the binding of hydrogen to oxygen in, for example, a silicate mineral that you might find in the soil. So all of these are water, but if you're an astronaut interested in drinking it, or a company interested in mining it for fuel research, for fuel, or if you're a scientist interested in researching, ices delivered to the Earth-Moon system by comets and asteroids, you want to know which of these things your mission is going to have to deal with on the ground. Are we talking ice, or are we talking water-bound in minerals? So far, our data don't distinguish it, though, because M³ was not expecting to find water. It was a mineral mapper. It was not expecting water, and so it cut off just before the place with the key information. But it's an exciting time because we're seeing the fact that, on Earth we have a water cycle. There's something of a water cycle on the moon. We have volcanoes or comets and meteorites, solar wind perhaps implanting hydrogen in the soil, creating water, then impact or heat or other things causing its loss. So Sarah Pooley from PCC created this graphic. It's a whole new field. We don't quite understand the water cycle on the moon. This is the state of the science here about the water cycle on airless bodies right at this moment. Part 2. Transitioning. Meantime, while everyone is scratching their heads about this plethora of new water data about water on the moon that doesn't quite all mesh up into a story just yet, meanwhile, there's a revolution going on in space, lowering launch costs, increasing availability of commercial off-the-shelf technologies are just increasing the number of countries that can participate in space exploration, the number of industries, the number of student groups at universities who are launching CubeSats and smallsats. This is a particularly outstanding example. This is JPL's, an image of Mars with the solar panel from JPL's Marco mission, which launched with InSight in 2018 and then traveled all the way, 2 spacecraft, traveled all the way to Mars on their own to serve as relays during the landing, snapping this beautiful picture. So it proved that something the size of a cereal box can go into deep space and that has the ability to make observations that could be useful for science. That's a tremendous accomplishment. So this idea that if you've heard of CubeSats and smallsats, the idea initiated initially in universities, including Stanford and San Luis Obispo here, although now it's mainly commercial. The idea was this. Every time that a rocket launches, almost every time, there's some amount of excess mass capacity in that rocket. Why? Because you buy the capability of the launch early when you're not quite sure what the performance is ultimately going to be of your spacecraft, what its mass is going to be, so how much up you need. As your development refines, typically your mass decreases, and that leaves a little bit extra that could be utilized if someone knew about it ahead of time. right? Because it takes a while to build a space mission. So the idea with these CubeSats was that you standardized the form factor. You made the interface standard so that literally it didn't matter to the primary mission. You could slot in anything. So it actually just takes advantage of an economic inefficiency to get more folks access to space. And these types of, you hear about some of these CubeSats in the news, mostly larger ones, 6U, 12U, this is 1U, so 12 times the size, are the ones that are forming some of the Starlinks as an example. And you can see the explosion in the number of orbiting craft, and this is in large part, at least over half of these are CubeSats or small sats. So as an example of another science application, and this one's just fun, so I show it, even though it's MIT. I mean, my colleague, Sarah Seeger, and colleagues at Lincoln Lab, and that team, along with JPL, built Asteria, which is an exoplanet hunter, same size as Marco, that 6U form factor, but this whole thing here, this long dimension into the screen, is a camera, and they used it to take pictures of 55 Cancri E, and guess what? They observed a transit of an exoplanet, the small little guy in space. I mean, Caltech could put up a satellite like this and look at our favorite exoplanet too, maybe even more. So in addition to CubeSats, though, I think something important is that this idea of standardization to facilitate rides to space has gone to a bigger size. Why is that important? Because it still is the case that for more mass, you can have a more capable scientific instrument, so you can start to do a lot. So another innovation is this ESPA ring, and there are other kinds of interfaces now as well, but this was among the first, where basically there was some primary spacecraft that bought the launch, so this is the primary spacecraft, this is the rocket fairing, but underneath it in the stack was this ESPA ring that as long as you were a certain mass and you sent in your model ahead of time so they could make sure you weren't going to mess up the primary, you could slot in here and send all different types and shapes of spacecraft into space to take advantage of that excess mass capacity. So again, it's kind of like not like Uber to space, but more like Uber pool to space, where you kind of have to wait for someone else to go, but then you can hop on the ride for less. So that brings us to part 3, water on the moon, small sats. NASA recognized the value of these missions, and this is where Lunar Trailblazer's origins come in. So the origin of Lunar Trailblazer is in a very constrained question, which is, what big science can you do with a small sat? Most of the time when NASA selects missions, it does it via competition, and this was no different. So there was an opportunity, the SIMPLEX, Small Innovative Missions for Planetary Exploration, pretty good acronym. So SIMPLEX had an opportunity where the box that your concept had to fit in order to be selected was that it was a ride-along mission, so you were hitching a ride. It was cost capped at $55 million. It was mass capped at a size that could fit on these ESPA Grande rings. It is a Class D implementation, which means they relax some of the NASA guidelines and allow more risk. But it was still seeking the highest possible science. So there's a National Academy's decadal survey once every 10 years. What is the highest quality science is described? Well, this call was seeking it, but under these constraints, okay? So the hypothesis, NASA's hypothesis, is that for select science questions that it is possible to do big science in these small packages. And this is where Lunar Trailblazer's origin lies. Now, why a mission to the moon? Why did that occur to me and team? Well, there's a special shout out here for Mark mentioned KISS, the Keck Institute for Space Studies. There's a special role here for KISS and Caltech, because when I came to Caltech as faculty, I had worked on Earth and I had worked on Mars missions. I hadn't worked anywhere else in the solar system. But my colleague, Andy Ingersoll, along with UCLA colleague Dave Page, and then postdoc, then later JPLer, Paul Hain, convened a workshop because they were interested in that water on the moon question. And I was like, oh, okay, sounds interesting, sure, I'll participate, when they asked me. And it was an exciting study because I had studied water on Mars. I had studied water in the rock record, what makes Mars habitable. But I realized that those same techniques that I was using were applicable to the moon. And indeed, it just so happened that other enthusiasts in the group, Barb Cohen at NASA Goddard and others, were also enthusiastic about small satellites. So it was recommended a Lunar Trailblazer nano satellite should be developed and launched within the next 5 years with a scientific payload for investigating lunar volatiles. 2013. That call came out in 2015, so we're a little behind on launching it, but we proposed it. The other part of the origin, and I think this is important to talk about for especially other early career scientists in the room, I was early career when I did this, is that there's a special role for the proposals that we don't win. Because sometimes that can be really important, actually, and those efforts, just by doing them, it is important. And in this case, Lunar Trailblazer actually came from, and I want to give total kudos to the team at JPL who led the proposal for the Moon Resource Mapper proposal, MRM, which was going to be, was proposed as a ride-along mission on the Korean Pathfinder lunar orbiter. We weren't selected, but we learned so much about the approach for how to propose an instrument to do spectroscopy efficiently on the moon. And so that is where Lunar Trailblazer came in. There's a lot of words on this slide. We're going to get to the pieces of it later. But Lunar Trailblazer is a small sat. It's about 200 kilograms. We're measuring reflected light. We're measuring thermal emission from the surface. And we are launching later this year with Intuitive Machines as a rideshare for a 2-year science mission from orbit to understand the form, distribution, and abundance of water on the moon and the lunar water cycle. That is to make progress in resolving some of those unsettled aspects about the state of science at the moon right now. And so in bringing this team together, I'm the principal investigator, but my project manager in systems engineering is at JPL, flight system at Lockheed. Our mission ops and student collaboration is led here at Caltech by IPAC, and we carry 2 instruments. One built at JPL, the imaging spectrometer. It's called HVM-cubed, the High Resolution Volatiles and Minerals Moon Mapper, after M-cubed, the one that discovered water on the moon. And then the Lunar Thermal Mapper at Oxford. So I'm going to talk about the science, and then I'm going to talk a little bit about implementing the mission. So the science is what motivates me, and the way that we have approached this problem of understanding water on the moon is really to think closely about where the gaps are. So we wanted better spatial resolution, so we could understand where the water was. We wanted that better spectral range to be able to tell what the water was. Enough signal-to-noise ratio to see in those permanently shadowed regions, and then simultaneously getting water composition and temperature at multiple times of day to understand, like, for real, is it changing in abundance as we look at different parts of the lunar surface? So the approach we take is to have just 2 instruments. We're a small satellite, can't do more, and we have them nested together. So for this image, with our imaging spectrometer, every single pixel in this image will have a spectrum that will look something like what's over here. And that will allow us to distinguish ice from those other forms of water, like just hydrogen stuck onto silicates, metal OHs. So we have the spectral resolution for every single pixel at about 60 meters per pixel to be able to tell. At the exact same time, to deal with that temperature issue, we have the Lunar Thermal Mapper over the area acquiring exact maps in every single pixel. What is the temperature of the surface? Oh, and by the way, at the same time, we added a few other channels, so we're going to be able to tell the different types of rocks that we're looking at, too, at the same time that we're getting the lunar water. So this is a pretty high caliber science measurement for a tiny satellite. I think in the interest of time, I'm going to skip over the formality of our goals and just say that the thing that we've had to design the most for is our most stressing measurement, is seeing in these shadowed regions. And here's some mission art from Joni Q, who's one of our PCC interns who drew this amazing photo that I think captures this ghostly ice in the middle of a permanently shadowed region. How do we see that ice? We're using reflected light, but I said the sun didn't shine. So what we're doing is it's actually a triple bounce. So we measure light hitting the walls of the crater that then scatters sunlight into the center of the crater, and then that is reflected from the ice deposit back to our HVM cubed instrument. It is a sensitive measurement to be able to do this and discriminate OH and H2O at low light levels. It's a 1 part per 100,000th measurement, so we have to be thermally stable enough to make this measurement happen. So this sounds pretty hard for a small sat. It is hard. It's been hard. Because this, really started as a hypothesis. No one's done this before. This is a new thing for NASA. Just to put it in perspective with some of the other missions that you may have heard about, I'm putting some of the other missions, the Perseverance rover, Europa Clipper, Psyche, Mars Pathfinder. Remember the little rover, 1997? Super cool, July 4th landing. Grail, which is a 2 spacecraft gravity mission to study the moon, and DART. You see DART? See that, the hitting the asteroid, right? Remember, wasn't that cool? Pretty cool. So Lunar Trailblazer would be the lowest cost planetary mission, ever. Big science in a small package. It's challenging, and it's been challenging. How do we do this? This is a lot of text, but let me talk you through it. We do it by a laser focus on the most important novel measurements. I talked you through what those are, but it's really being very precise about what is not known and what kind of measurement is needed to make progress, and not being able to do much of anything more, right? You have to stay laser focused on the science goals. And then the other is really being scrappy in terms of how can we leverage different things, different aspects. So we were able to, HVM cubed built on the legacy of the Moon Mineralogy Mapper. Colleagues at JPL had applied for grants and miniaturized M-cubed, Rob Green, Diana Blaney, Zakos Maroulis, others. We couldn't afford in that cost cap to have more than 1 US instrument, so I called up my buddies at the University of Oxford, where you heard I got my master's, and I'm like, hey, do you have a thermal camera? Do you think the UK Space Agency would want to contribute it? And they said yes. We couldn't get a top-of-the-line comm system, so we really focused our science measurements on making targeted observations of places on the moon that we knew were interesting. And for the allowed mass, we can't do a direct-to-the-moon burn cruise. I'll show you what our trajectory looks like later. We can't do an Apollo hard burn in and just a few days. And then we've called on unique capabilities that this campus has and that our sister campus, PCC, has for an ops center here, using the heritage of Caltech IPAC with telescopes and undergraduate students. And then allowing some risk to save on cost. This is a risky mission. It's single string. We can't afford to have a lot of redundancy on the spacecraft. So we're just going for it with what we have and testing as we will fly to make sure things work. And then people really matter. It takes a small and dedicated team. And these are just a few of the folks on that team. It takes a village to make a space mission. These are the people who are in the Pasadena area and my science team. There are hundreds of people who have touched Lunar Trailblazer in some way, and I'm amazingly grateful for their efforts. So one doesn't normally show a nerdy organizational chart in a talk like this. I'm going to do it anyway, because I think it illustrates just how does a mission work anyway. So I'm the principal investigator at Caltech, but we've got a whole team over in the planetary science office, over in contracting, and in the Office of Sponsored Research that helps our business and our systems engineering, safety, mission assurance, project management is at JPL. And then there are all these pieces that have to fit together. So I'll talk you through what our mission design and navigation team is doing that contributes to our operations, how our instruments have been put together, and then finally how they all get put together on a spacecraft. So this is what's happening for each of those pieces of our mission that is doing something. So this is what our trajectory looks like. It's a representative one. It's not going to be exactly like this. But we launch, and we actually have to go past the moon because we're coming out so fast. We have to do a trajectory correction maneuver because we're riding along with a lander. We do a trajectory correction maneuver to avoid hitting the moon. But our propulsion system is not like hefty and expensive and has enough delta V that we can like do a hard burn like Apollo did to get there in 3 days. So we shoot way past the moon and then loop back on these low energy trajectories to eventually spiral down and insert into lunar orbit. So instead of 3 days to the moon, depending on the exact day of launch, it's going to be 4 to 7 months to get into our science orbit. Once we're in our science orbit, we're in a polar orbit, and we're looking off to the side, and every once in a while, taking an image as a target of interest passes by. So we're push brooming across the surface. When do we take an image? When do we do an orbital maintenance maneuver? All of that will be done here on this campus, and this is exciting. I am unaware if there's a previous planetary science mission that's done operations from a university campus. So Caltech IPAC has a legacy of operating space telescopes and is taken on the planetary science spacecraft operations, working with JPL mission design and navigation, as well as Lockheed Martin for engineering support. This office space was transformed into our operations center, where you can see Lee Bennett and the entire MOS team here working on operations readiness tests, getting our spacecraft sequences up and ready. One of the innovative things that we've also done, which is both a training opportunity as well as, frankly, a cost savings, is to have infused students into the mission at all levels. You've seen a number of the graphics that have been produced by the science and art students at PCC. We have computer science, physics, and other folks from both Caltech and PCC who are doing things like staffing consoles, talking to the Deep Space Network on behalf of our spacecraft, who are designing telemetry, who are examining that telemetry, who are working on science scheduling software, who are creating the graphics. I got started on a space mission as an undergrad, and this is a great way to do it. Just to show you some hardware pictures, our instrument, our imaging spectrometer, takes in light, sends it through a spectrometer, and that rainbow pattern is what reads out the spectrum. There is some amazing technology under the hood enabled over at JPL. What is amazing for me as a PI is when the PowerPoint that you put in with your mission proposal 4 years later is a piece of flight hardware that has exactly the performance that you wanted. So the JPL team did that with HVM cubed. We've done that with our lunar thermal mapper over the last 4 years. This is Rory Evans, member of our team at the University of Oxford. He's doing his PhD on the optics of the lunar thermal mapper instrument, taking it from PowerPoint to full assembly to delivered flight instrument. Similarly, over with our contractor Lockheed Martin, we've taken our PowerPoint spacecraft and its configuration on the ESPA ring, where a plywood box was used to check the lengths of all the harnesses that were going to be connecting all the components. Well, that was then built out into panels where that harnessing goes on the actual flight panels. Here's our propulsion tank, which will fit in here. You see that we're actually almost all prop tank on this mission. Here's the installation of HVM cubed on the vehicle. Here is the vehicle in our flight system here in the thermal vacuum chamber. Here's some of the team posing. What it will look like when we're out in space with our solar panels deployed. That's about a 3.5 meter wingspan. Here we're on the spin table, first integrated, and now wheeling off just this January, where as of a few weeks ago, we're sitting on the vibe table, shaking it, trying to make sure that everything's gonna be working when we get to flight. So what lies ahead? I'm out of time here, so I will say that we are here in our development. It's been a journey from selection here in 2019 to the future, but this is where we'll be nested on Intuitive Machines number 2 on the stack here. For those of you watching the news, Intuitive Machines number 1, the launch window opens on February 13th. Wish them well, because that will help our ride on Intuitive Machines number 2 stay on time. We'll be loaded at the SpaceX processing facility at Cape Canaveral onto the rocket. and then launched into space in November this year. So I'll leave it at that, and I will say that I am incredibly excited to share this mission. Lunar Trailblazer is really pioneering this small satellite approach to planetary science, investigating one of the most important questions about water on the moon. We're doing it in a way that we're bringing students along on this journey, starting their careers, and it's going to be exciting. So hope you follow along. Check us out. If you're a student, we are until Sunday taking applications in the next Lunar Trailblazer internship pool. Check it out. Thank you.
Thank you so much, Bethany. I mean, like, what an amazing behind-the-scenes look at everything that goes into sending things into space. My goodness.
It's fun. Yeah, it's not been dull. As you might say, there's a lot going on, even though it is a small satellite.
So I have a bunch of questions here, and I would love to have more questions. So don't forget, take a picture of the QR code with your phone so that you can submit questions for Dr. Ehlmann. And if you are more old school, we have a few ushers that are floating around with comment cards, and we'll make sure that we get those uploaded so that I can ask Dr. Ehlmann. Okay, we have a lot of very interesting questions.
Sure.
But one of them I think that I actually had as well is, what's the predicted lifetime of the Lunar Trailblazer?
Right, so Lunar Trailblazer's nominal lifetime, so under normal circumstances, is 2 years. Mm-hmm. After that, there's a possibility of an extended mission if things are still working. Most of the components we've tested to about a 5-year lifetime. You know, you test with margin. Mm-hmm. So the most limiting aspect is, unless something breaks, is the fuel. The moon has actually a lumpy gravity field, and so we have to stay in this fairly close orbit. We have to make orbital maintenance maneuvers every 3 to 4 months or so, and at some point we will run out of fuel, at which point we will crash into the moon.
So that's the determination.
If all works in our components, that's the fundamental lifetime limiter. I mean, as a function of, this is a high-risk endeavor because we are using commercial off-the-shelf components and sort of trusting, like, as they're delivered as is, and that this one is similar to the one that we've tested over here. So the fuel is our fundamental limitation, and the rest of the spacecraft follows.
You get what you get.
You get what you get. That's right. That's what you get.
So between orbiters and landers, having worked on both, what are some of the primary differences between those two types of missions?
Landers are a lot, I should say rovers. I've worked mostly on rovers. Rovers are a lot more hands-on. It's like every day you're operating the rover and getting data back and then making decisions about what to do and feeding that back and forward. With an orbiter mission, you have the luxury of being able to sort of like plan ahead. Orbital mechanics is more predictable than like rock position on Mars in terms of whether it's going to move when you touch it or not. So that is one difference, is that the cadence of planning can be a little bit more deliberate and carefully planned out. But beyond that, it's a space mission. And in the same way, you have to pay attention to the details of the hardware, the details of the science. I think in many ways it's very similar.
I really love this question. So of the 3 forms of water that you mentioned, which one do you think you're most likely to find first?
Oh, first.
Yeah.
First.
Or likely to find.
Well, okay, so
whichever question.
yeah, I think so one of the aspects that I didn't talk about the details of what Lunar Trailblazer is going to be doing, but as soon as we're out of Earth's atmosphere, and within a suitable distance of the moon, that the moon is going to fill enough of our, field of view to make it worth taking a picture, we'll take a picture with our spectrometers, right? And at that point, we're going to be looking at the sunlit moon. And so I think we'll detect the metal OH or the H2O we'll be able to tell which it is, which is exciting. That's on that sunlit side of the moon. I don't think that's going to be water ice. I will be tremendously surprised, and it will be the source of a new Watson lecture if it's water ice. But on the sunlit moon, it's probably metal OH or bound water molecules hopping around. And I think we'll be able to tell that before we actually even get to the moon. Because once we're out of Earth's atmosphere and the blocking effects of water vapor in our atmosphere, we'll be able to see that almost immediately.
It'll be really rewarding. You don't have to wait for it to be fully in place.
Yeah, so we'll have something to chew on during that 4 to 7 months before we get to the really high resolution images, yeah.
Exactly.
Yeah.
What are some of the more technical challenges that you're facing now in the mission?
Yeah, I think some of the biggest challenges are in integrating the pieces of the system together, like interfaces. We have to have particular, connectors on our harnesses working perfectly with our flight computer, all seated in there, all tested. We have to have the guidance, navigation, and control software developed at Lockheed Martin working with the Caltech FlatSat so that the procedures developed by the ops team work. So there's all these pieces that have to be coordinated in this intricate dance to actually make a space mission happen, and that those interfaces are some of the most challenging aspects.
Yeah, sometimes I find with technical missions, some of the biggest challenges are people.
They can be. In this case, though, I'm not just saying this, we have a great team. So my challenges are not people. My challenges are cantankerous interface components and money, because money is always tight on this mission. It is by definition tight on this mission. I think, however Lunar Trailblazer turns out, I think there are going to be a lot of lessons learned for how to do this, right? We are the first of this new class of mission, and so some of the challenges relate to that newness.
When you're successful, what do you think the next small space mission doing big science should be?
Oh, well, that's a fun question. I bet there are some people in the audience who have small satellite space missions that they want to do somewhere else.
So I'm asking you.
You're asking me. Oh, there's so much that's good to do. This is why I'm so excited about this mission class, right? Because, you can go to so many destinations. I think Venus is incredibly exciting. I think you could do a small, probe or flyby into the Venus atmosphere, complementing what the Da Vinci larger mission is doing to get a few more data points, not just one profile, right? You'd learn a lot if you do one profile, but more is better because planets are not all the same everywhere. So flybys of Venus, I think one could do some studies of water-altered asteroids in the asteroid belt. Check out water and alteration. I think you could send a small satellite to Mars, actually, and really improve our understanding of the geologic mapping using some instruments that are pretty similar to Lunar Trailblazer. So those are some immediate targets. There's a lot of ideas, though.
I can see your face lit up.
I love the exploration part of it, right? I'm a scientist who's driven by, my particular flavor of science is driven by new data. By figuring out what the right questions are and then figuring out how to answer them by getting data from our missions. So I love thinking about new missions.
I've been asking some technical questions, but this one keeps getting upvoted, so I'm going to ask it. What is your favorite space movie?
Contact.
Why?
Thank you, Contact fans.
It's a good one.
Yeah.
Why?
Oh, I just love the main character, Eleanor Arroway, and her drive to just understand and to know, even in the face of fear, in the face of all kinds of challenges. That desire to know is just something that really resonates deeply with me.
What have you found surprising about working in this field? You mentioned some of the work you did as an early career investigator, and now kind of having seen many different types of missions and worked on many, many different projects. What has surprised you about things you've encountered in your career thus far?
I don't know if surprise is necessarily the right word, but I guess I've come to appreciate, and it relates to I've come to appreciate how important people are.
Yep.
right? We like to think of these space missions and we think of them as people sometimes, like the Ginny helicopter, right? But really, the space missions are all about the people behind them and getting those people to work together as a team to just do something greater than any of us can do on our own. So as I've moved from the period where I was either just, saying, hey, we should do this type of mission, or I was using mission data to actually being the person who's working with a team to execute the mission, you really just realize how important the conversations are, the setting up of communications in a way to make it all happen.
Not whose idea was it, but I was really impressed by the combination of art and science and kind of helping to imagine what this mission really could provide in terms of data. Where is that collaboration generated from, and how else is it being used?
Yeah, I mean, it's a small mission with a small budget, but in thinking about, well, what could I do? What could my mission do? The idea of involving not only our Caltech students, our wonderful Caltech students, but also, there's a 30,000 person institution just kitty corner to us, right? We could get Pasadena City College students involved too. And so everything that we're doing with science and art has just simply been at that interface of professors at PCC, students who see the advertisement applying, who then work within our science team on topics that we think we need to communicate the mission, to communicate how we're doing our science, to communicate what's exciting about it, and just help people get the vision for what it is that we're working on. And I think that's actually so important. It's part of imagining the future. And to do something, to shape the future, you first have to imagine it. And part of that is visual.
Yeah. What does finding water on the moon mean?
It means different things to different people, right? So for me, I'm just driven by the curiosity primarily to understand, where did that water come from? Because I didn't talk too much about this, because that would be the hour-long version of the talk. But the Earth and the moon formed initially. They had some amount of water, but we really think that most of the water on Earth came in later. It was delivered by asteroids and comets. It was degassed from our interior in volcanic eruptions. And Earth, though, is a very active place, so most of that ancient record of what happened when has been destroyed. It is possible that in these permanently shadowed regions of the moon, there are water ice deposits that are billions of years old. And that would be a record of the delivery of water from asteroids and comets into our little Earth-Moon system. That has implications for our own planet. It could alternatively be a record of volcanic activity on the moon, which would be pretty cool if you could see how the volcanic gases coming out evolved over time. So I'm driven by that scientific curiosity about, how does it work? Why is it there? I think equally, though, there's a lot of excitement from our human exploration in terms of the idea of a moon base, right? You could have water, you could drink it, but actually more important, I think, for the lunar resource piece of it is if you have H2O, you can split that, and then you have H2, and with a little chemistry, O2, and then you put that back together, and that's rocket fuel. So there's an aspect of an interest in mining some of the moon's water in order to create rocket fuel that could then send us out to other destinations. Why is it important that it be on the moon? Well, it's outside Earth's gravity well, so you don't have to burn a lot of rocket fuel to use the rocket fuel. So there's this idea of a whole lunar economy, potentially based on water on the moon. I think we do not yet know how much water is on the moon and how difficult it is to get out. And that's why I think Lunar Trailblazer is an important mission, so that we actually understand what quantities are we talking about really, and where is it exactly? It's a very interesting time between the science interest and the commercial interests.
We have time for one more question, but before everybody gets up, I want to remind you that February's Watson Lecture is actually next week, so please make sure you sign up, register for next Wednesday evening, where we'll be hearing from Shri Kulkarni about the Zwicky Transient Facility, so that should be really, really good. Okay, final one. When we're talking about water, we are human, we like to think about biology. Is it possible that there is life on the moon, if there is water on the moon?
Yeah, so this is one of these cases where you really need liquid water for there to be biology, that solvent, right, to help facilitate the chemistry that powers us each and every day. And so if there's water on the moon, it's going to be solid or it's going to be gas. So in this case, we are not talking about life on the moon. We're talking about water for scientific sake or water for commercial sake, but no life in this case.
Okay, in this case.
Although I am a huge fan of the search for life in the solar system, that is not this particular mission. Maybe a future Watson lecture.
We wish you and everyone else on this mission and on your team just all of the best quality data that you could possibly receive. No noise, all signal.
All signal.
And a wonderful time.
Great.
Thank you so much for joining us.
Appreciate it.
Thank you so much. Thank you all so much. Please feel free to join us outside for tea and coffee and conversation.